Greetings and welcome back. So, this is the final vignette in the part of the course that has to do with representations and vectors and collective coordinates. And we end on a very, very high note. So, just as a preface, I wanted to comment on, I guess, many long years of experience in the world of science and the notion of peer review and the notion of how we react to each other's work, and specifically a kind of course which is offered at various places, perhaps even the one where I work, which have to do with how to critically read the manuscript. And I say that with a touch of sarcasm in my voice because I think that I'm actually more interested in loving papers or learning how to figure out what people are saying without worrying in the first 3 seconds about whether they did their controls or that kind of stuff. Just to give people the benefit of the doubt and just to do the hard work of figuring out what it is they've done. And a more sort of simplified way of saying it is to be a lover rather than a hater. And the reason I bring that up is because this is one of those cases. So I read probably 150 papers a year, and in general, I keep a single paragraph outline of each paper, and the ones that I really, really like get a special color in my notes. And the topic we're going to talk about today is certainly one of these masterpieces. So, speaking of being a lover, I marvel at Charles Darwin. I think that it's strange in some sense, our relationship with older literature, because the simplest thing to say for me is that one should not have an opinion if you haven't actually visited the literature itself. And so, I think that Moby Dick is this fantastic book, but until I read it, which was in my 50s, because when I tried to read it when I was younger, I just couldn't tolerate it, having an opinion about it seemed unfair. I haven't read the book. I haven't, and even if I have read the book, I should probably be cautious about having a very strong opinion because it's as much about me as it is about the book. So, why do I bring that up? Because Darwin is a remarkable character, and I'm not saying that out of some hero worship or mythology because I find that very annoying. But just for example, a few years ago, I had the chance to visit several different very famous places for coral reefs. One of them is French Polynesia, the other is the Maldives, both times on boats. And while I was in French Polynesia, I read Darwin's book on coral reefs basically from cover to cover, and just urge you to go take a look at it. And in particular, take a look at the maps, if nothing else, just to see his understanding, in the middle of the 1800s of the nature of reefs around the world. And his first theory actually was a theory of coral reefs that explained for somebody like me who's a surfer and very interested in reefs, the difference between a typical coral reef like you'd find on the north shore of Oahu, a barrier reef like you would find in Tahiti, and an atoll like you would find in the Maldives. Those are three different life history stages of oceanic islands and their surrounding reefs. So this particular book, The Formation of Vegetable Mold Through the Action of Worms, is Darwin's last book. And, what I find kind of amazing is that you look at his table of contents, and the way I feel about it when I look at his table of contents is this is a person who notices things. He's out in the world, he notices things, but he trusts those observations. He turns them into content. So here you see that in chapter 1, he's talking about earthworms, and he notes that they're sensitive to heat and cold. And that's going to be relevant for what we're going to talk about today, because I'm going to tell you about this beautiful thing from Greg Stevens and company where they basically analyzed the behavior of C. elegans, and one of the perturbations that they offered it was temperature. So, for many of you that know or have watched any of my vignettes or know me personally or whatever, then you know that I'm very keen on the role of estimation in science. I believe that it's underappreciated or unappreciated. People trivialize it, people scoff at it, and I think history is on my side on this one. They don't know what they're talking about. I'm sorry to be so strong on my words, but Darwin basically here, in chapter 3, the amount of fine earth brought up by worms to the surface. What a great topic. And so I give a homework in freshman biology at Caltech where the students are urged to actually visit Darwin in his garden and to have a go at trying to look at this question. And so one thing you could do is you could you could watch this video. I gave the Vimeo link, but this is the action of earthworms over some time scale like a week. And this is the kind of experiment that you could do. And I guess it reminds me a bit, just a plug in passing, another lover versus hater thing. There's a guy who I know and like very much named Michael Bain. He's a professor at Harvard, and when he was a postdoc, if I remember all these things correctly, he was working with Roy Kashoni, and they built an experimental apparatus for watching bacteria grow into increasing concentrations of antibiotic. And it's a macroscopic experiment, a bit like that worm experiment. That's the reason I'm making this point. Super interesting because I think, maybe initially it was designed as an experiment in basically an educational context. Of course, I deny that kind of thinking right from the outset because research is a kind of learning. It's learning about the unknown, and in this case, the unknown was the nature of evolution of antibiotic resistance. Anyway, so check out this Vimeo thing. If you have kids, small kids, you might take a used clear soda bottle and then fill it with dirt and put a couple worms in, and you can do this for yourself. And we basically ask the students to, on the basis of a video like that knowing the time scales and knowing the volume of a worm and so on, to estimate the amount of earth turned over by worms. And you can do this at all scales, a single worm in a bottle like that or across the whole world and so on. It's very, very interesting, and I think it's really worth knowing. So this particular vignette is about the dance of C. elegans, and so I'm asking you in your mind's eye to imagine the slithering motion of this worm. You're watching it on a microscope, and the data is going to be basically the position and shape as a function of time. Although those are kind of fancy words, really, for something much more naive, which is watch it move. That's really it. The data is a video. So that's what we have. We have a movie. And the whole story, in some sense, of this quite remarkable and beautiful paper is to take those movies and to do what it is that we've been talking about for the last 5 or 6 vignettes. In other words, in some incredibly clever, imaginative, creative way, to come to terms with that high-dimensional data called, 1,000 by 1,000 pixel movie. So, each single image is 10 to the 6th pixel intensities. So, and then let's say I did that regularly while it was moving. So that's the data. I really want you to digest that. The data is a million numbers for every time point. That's the data. And, I really like to make a big deal about this because I'm going to say this is not directed at all towards Greg Stevens and company. I've told you already, I love this paper. It's brilliant. But this is directed at all of us. What's stupid data? A million numbers. It's horrific. I don't want that. I want a story. I want to be able to turn it into a narrative. And these people propose to find basically a 4-dimensional representation of that using the trickery that we've been talking about. And how gorgeous is that? I should just note in passing, in case you grab this paper, right on this very first page at the lower right is an equation or 2 equations, the so-called Frenet equations, and one of them is a statement about the time derivative of the position, and the second one, and so this is proportional to the tangent vector. That doesn't belong. And then the second equation is supposed to be dt by ds. And unfortunately, there's a typo. This is not the fault of the authors. I'm willing to bet. Maybe they made a mistake in their LaTeX, or maybe it was the typesetting, or it doesn't matter. But anyway, I'm telling you this because I just want you to notice the second equation should be this, and instead the left-hand side will be dx s by dt. This is not a critique. I am not critiquing. My first book, Crystals, Defects, and Microstructures, has some free LaTeX equations in it. You know, anybody that's actually tried very, very hard to rid their work of errors will just, you know, consult the second edition of Feynman's book on path integrals and look at the preface where the guy says he corrected more than 700 errors. J.J. Thomson did the same for Maxwell. I'm just saying, you know, like, of course that we want attention to detail, but errors are inevitable. Okay, so here's the game. The game is this. We are going to instead, we're going to take that data and in imitation of Stevens and company, and we're going to replace it with already a lower dimensional representation. And that lower dimensional representation is that we're going to discretize the contour of the worm into 100 data points. And at each of those points, we're going to find the angle theta. So we've taken the million points, the million numbers, and we've replaced it with 100 numbers. That's already a 10,000-fold reduction in the number of degrees of freedom that we use, that I call you on the phone and I say, hey, here's a million numbers. That's the worm at a given time instant. Now I call you on the phone and I say, hey, I have found a better way to do it, and now I'm going to tell you 100 numbers, and that's these angles theta. That's good. That's very, very good and extremely provocative and interesting. And then what we're going to do is we're going to say, let's do better than that even. Let's actually try to find collective variables. And when I say collective variables, this is sometimes you could use the word, we're doing a coarse graining. Coarse graining is not laziness. Coarse graining is not naivete. Coarse graining is sophistication. It's depth, it's insight, it's intuition. The reason I say that is because I've heard out of people I admire's mouths, I hate coarse graining. The thought being that, you know, this is back to being a lover and a hater. Don't be a hater when you don't even know what you're talking about, you know? Like it's a meaningful thing. It goes back to these beautiful ideas by people like Kadanoff on decimation of spins on lattices. It isn't some sort of vague notion. It's concrete. So we're going to take it a step further. So in passing, just to show you figure 1 of the paper, their argument, there's a nuance here that I'm not going to spend any time on, which is that they rotate the coordinate system so that the average angle theta is 0. That's cool. I like that because you might remember that the covariance matrix asks us to subtract off averages and things like that. But this is a technical point. The main thing is the replacement of the worm, the replacement of the million numbers by a contour, and we're going to parameterize that contour by the arc length s. S, let's say, runs from 0 to 1, s being equals 0 being the head, s equals 1 being the tail. And so I tell you an s, that's a distance along the contour, a normalized distance. So it's x over L, or whatever you want to say. And at that point, there's a theta. So that's what we've got. So I wanted to give you a little bit of a sense. We give this as a homework in freshman biology at Caltech, and I'm very excited about giving it as a homework. And I think, you know, some fraction of the students, it's intimidating if you let it be intimidating, but it's really a guided tour. I mean, this is tourism, and it's a guided tour of how to do this sort of dimensionality reduction. So what we do here, and what I'm trying to show you, is some of the steps. So first, you know, we have this image data, and the next thing is you choose a threshold. You know, that's a standard maneuver, which I think is really cool, just in the sense that even that raises all sorts of ideas about dimensional reduction, and, you know, what does it mean to get rid of redundant nonsense? You know, I told you these million numbers, it's mainly nonsense. So I don't want that. I want to find a way to reduce it. Then there's this skeletonized. So that's, you know, turning this into the contour that I already mentioned. And then we have the all these positions. We can compute the angles. You see that right here. And we can plot the angles. That's amusing. And then we construct the covariance matrix. And, the essence of what I wanted to say is the covariance matrix. I'm just trying to give you a schematic of what it is that this thing is going to be producing. So I'm going to show you the matrix element Cij, and I'm going to define that as this theta I, how do I want to think of this? Minus theta, some sort of theta bar times theta j minus theta bar averaged. So what we're trying to do is we're trying to ask about the correlation between the angle at one point along the contour of the body and another point. And you can imagine, if I is almost equal to j, then those two angles are going to be roughly the same. If I walk a little bit farther along the worm than the other part, because it's got this sort of sinusoidal look to it, it's going to be pointing over here. So they're going to be anti-correlated. In other words, as I walk along, the correlation is going to ebb and flow. And so, the thing that's quite amazing here is that, we can compute this correlation matrix, covariance matrix, and then we can do the procedure that I have now shown you several times. I showed you first in the context of the coupled motion of masses and springs. That was a two-dimensional example. We actually literally computed the elements of that 2x2 matrix. The covariance matrix was a 2x2 matrix. We found the eigenvectors and eigenvalues, and it told us what modes were under the surface, the symmetric and the antisymmetric mode. Great. Then we did gene networks and transcriptomes. And what I showed you there was, I can show you what I showed you. So, we did stuff like this. So we got ourselves the gene expression matrix, and then we computed the covariance matrix, and then we found that there was a nice coordinate system, which I hate these words, but I'm going to say them, which explained some fraction of the variance. That's the way people talk about this. The reason I don't like it is because our goal in life is not to explain the statistics of variance. The goal is to understand our problems and to have intuition, and I don't like that as our metric. I mean, it's fine to have a quantitative metric, and that's anyway. I'm going on a rant, which I should not be doing. So back to this. Say it again. Wow, job well done. Amazing. Such a beautiful piece of work. So creative and interesting. And it just illustrates this idea of what does it mean to cleverly find a dimensionality reduction? And that's the answer is right here. So you undergo this procedure that I just mentioned. And what their assertion is that the four first eigenvalues and eigenvectors essentially suffice to tell this story. And I want to make a plug to my friend and book co-author Julie Theriault, who has several papers. I think I mentioned this already, but I'm urging you as a listener to go look at them. And maybe I will just, as a little advertisement, do a little vignette that just shows the data. But she looked at the shape of Colobacter cells, if I remember correctly, and then also at the motion of keratocytes, and used exactly this kind of dimensionality reduction. And she also, I think, found something like 4 or 5 principal components sufficed to capture the essence of the motion of keratocytes. So here, what they're telling us is that 4 of these eigenvectors essentially suffice to capture the motion of the worm. And what that tells me as a theorist, if I'm putting on my theorist cap, it says, hey, you can make a four-dimensional model. Actually, you probably can do two. So two of your modes will probably suffice as a first cut to describe the geometry of this thing while it's moving. The other thing is, notice that what we're doing is, this is about representation again. We've taken this million numbers, and we figured out a way, or they figured out a way, to collapse all of that to four numbers. And those four numbers are the weights, how much I mix u1, u2, u3, and u4 of S, the four eigenvectors. In other words, I have these functions, u of S, they're shown right here, and I mix them. I make a linear combination of them by choosing these weights A1, A2, A3, A4, and now I have represented the million numbers, called my horrific image that comes from a camera, and I can build a theory. I could build a theory of the A's, dA1 by dt, dA2 by dt3, dA3 by dt, dA4 by dt. And those of you that know some quantum mechanics might actually think of, when we do perturbation theory, we write a wave function as a superposition of some basis. Like my favorite example is to write the molecular wave function as a sum over s orbitals. That's kind of the simplest version. This goes under names like tight binding Hamiltonian. It doesn't matter, but then I can do perturbation theory. I can try to find dAs, how those vectors change over time. You can find that in volume 3 of the Feynman lectures on physics. You can find it in the 1932 Quantum Theory of Radiation paper by Enrico Fermi. All of these are examples of, you start with something, it's kind of objectionable in the sense that the mathematics is messy or whatever, and you map it onto a new problem. And what I'm saying is, d coefficient by dt is one of these glorious things. It's one of these ideas of, excuse me, taking our representation and making something really cool of it. So, here what they're showing us at the top is the probability distribution on A1 and A2. And so this is wild, because basically it's telling you that how I'm going to mix A1 and A2 to get a legitimate version of the worm's motion. What else do I want to say here? I just want to, in passing, call attention to another beautiful paper, another one, it's another lover, not hater thing. So, Dan Goldman is another one of these people. So Bialik is somebody in that previous paper, Greg Stevens as well, but Bialik, somebody worth listening to. It's just, bottom line is, the way I would put it is, like, if he's talking, I want to listen. Same goes for Dan Goldman. If he's talking, I want to listen. I'm not going to sit around and micromanage and ask whether Dan did his controls, because I have seen N papers by this dude, and I know that if I talked to him, and if I had some objection, he would just explain it to me. But in general, they're careful. And sure, could I have a better idea? Could I tell him something like, hey, you didn't think of that? Probably. There might be a circumstance, but that's not the goal of me reading somebody else's work. My goal is to find out, what did they do? And so this is just a beautiful thing, because what Dan is up to here is trying to invoke these ideas from people like Frank Wilczek on geometric phases, super sophisticated, cool things. I just want you to note, that they're thinking about the same sort of thing. There's position space at the top, shape space at the bottom, low-dimensional representations. And here, they're seeing a unity in the motions of all sorts of different animals. I just think that, that's really quite glorious. So I wanted to just show you, and you're welcome to send me a mail if you'd like to see this, but this is what it looks like. Thank you so much to Gabe Salmon for putting together this beautiful thing for my freshman biology homework. But we're trying to discover eigenworms. So I love this notion. Madhav Mani is always talking about eigenequations or eigenideas. And I think this is really, really fantastic. Like, what are the eigenideas of your field? What are the eigenequations? And here, it was no accident. Maybe I went past it too fast, but, more kudos to these guys for this paper. I just want you to notice, they called it eigenworms, and that's what we call it in our homework, and that's what I want the students in Bi 1 at Caltech to take away, is this idea of eigenworms. So, here's a sketch of what I just told you. So you take the data. We have the movies. You input it. And, this is the sort of thing that I'm perfectly happy to have somebody else tell me, here's a chunk of code that grabs those images and inputs them so that you can work with them. Next is there's a raw image frame. And now we threshold. The kind of thing that comes up here, you already know this. You're gonna want to get rid of this stuff because it's not part of your story. Those are wasted pieces of the million numbers. I mean, it's some schmutz that's on the cover slip or whatever. It doesn't matter. Then what we're gonna do is we're gonna contourize this thing. So now we found the worm. We're going to replace it with this contour. Now we're going to start doing things like calculating angles and covariance matrix. Now this is exactly what you saw in the Stevens et al. Thing, because you're seeing that the majority of the weight is in these lowest modes. All these other guys really are not bringing anything particularly interesting to the table. And then maybe here Gabe is using that language, fraction of the variance explained. Bleh. But you can see the fraction of the variance that is explained is if you use 4 modes, you're basically there. And then this is how to think of the modes, and you make linear combinations of them and assemble them in order to figure out the motion. And one of the things that's proposed in the Stevens et al. Paper is trying to build a theory of the mechanics, and I'm going to call it the mechanics in those degrees of freedom. Okay, so what's the summary here? So we've spent a good long time looking at vectors and representations and collective coordinates, and the key ideas that I want people to take away from this. Forever, we've been doing this thing of representations. It's one of the crown jewels of mathematical physics, of mathematics, of science in general. And I'm a big fan of 19th century partial differential equations, Fourier series, Bessel functions, all that stuff, spherical harmonics. I had no idea when I took my first physics class at WashU, which was classical electrodynamics using the book of Jackson. I had no idea what all this stuff about spherical harmonics was. And I probably still don't to some large extent. But it's really beautiful. How do you represent functions on the surface of a sphere? So people were very good at this, representing some mess and finding a way to represent it with some vector, the vector meaning the coefficients. And that comes up again and again and again and again and again. The advent of computers allows us to do this in different ways. I gave this little bit of a discourse on finite elements, which is one that I know very well. And, there what we're doing is we're replacing some function by something absurd, which is a bunch of straight lines interpolations. You're interpolating with linear shape functions. And yeah, it works super well. So here, the beauty of this is that there's a formal procedure, namely principal component analysis, that can be used to take some data and to try from that to figure out what the collective coordinates are. And I hope you were intrigued by the mechanics example I gave, meaning the mass spring system, which seemed out of place perhaps in a biology discussion, but it's not. And it's not out of place because there, using mechanics, F equals ma, we find normal modes. Those are collective coordinates. Then we took the exact same data and we found the collective coordinates as a data analysis problem by using the time series. We diagonalized a little 2x2 matrix, as we did when we solved the mechanics problem. This time the 2x2 matrix was data. And what popped out on the far side was our collective coordinates, the symmetric and anti-symmetric modes. Very powerful and extremely interesting. Okay, then from there we went to the case of the transcriptome. And the words that I want you to have in your head, my expectation for the field, my dissatisfaction. Dissatisfaction is not a criticism. There's nothing wrong with wanting to do better. I love what people have done. I'm deeply, deeply impressed with cell atlases and with transcriptomes and with RNA-seq, all of it. I love it. I love it. But don't ever expect me to show up and say, yep, we're done, good enough. Not happening. I want to do better. So the better is I would like to have a theory of the transcriptome. And as a starting point, what we did is we made a synthetic transcriptome And we played around with these type of PCA ideas to try to see if we could observe or find some collective coordinates. If you want to read more about this, take a look at papers from Madhav Mani and Friedman, where they really did this. This is what inspired Hernan Garcia and me, was this paper from Mani and Friedman. So once again, in the mode of being a lover and not a hater, that's really, really clever. So theory of the transcriptome. Then we turn to this example, again inspired by a great paper. In this case, the great paper is from Stevens, Bialik, Ryu. I missed the middle author, Bethany, who I don't know. I know the other three. And the four of them wrote this amazing paper in which they asked the question, and I like thinking of visiting Darwin or Newton in their studies. So we visited Darwin in his study, thought about the behavior and motion of earthworms. That led us to C. elegans. Maybe we can think of that as visiting Sidney Brenner in his study. And what they proposed in their paper was this beautiful way of looking at the motion of C. elegans using the tools of vectors, representations, and collective coordinates. And what's on the screen right now is a statement about collective coordinates. So I hope you were as amused by this as I was. I hope it inspires you to go out and try this for yourself. Frankly, it inspires me to go revisit this homework, which we give in freshman biology this year. When we do it in my class, I'm going to probably give a longer lecture. And I have to say, in the era of the chatbots, this is one of those things where the chatbot superpower, I have both positive and negative things to say about this, but in which the chatbot superpower can really help you. And what I mean by that is, like, put on be your most critical self, not critical of work of others, but just critical of yourself, critical of the chatbot, critical of, did I get this right? Take the data and actually do what I just showed you from A to Z. Dot every I, cross every T, and when you're done, you will be deeply impressed.